Hello everyone, welcome back to the latest lecture session. Until now we've been discussing the variables of interest to us, the relevant flows of interest to us and how the flows change with time or day, right? And then we moved on to discussing the headworks or the preliminary treatment. As in, we know that sewage typically is collected by gravity at the sewage treatment plant. If that is not permitted due to the relevant terrain, sometimes you will have pumping stations. So, at this particular sewage treatment plant, you obviously need flow of water from one unit process to the other. So, you typically do not want to pump it each time. So, you will want the flow to go by gravity or be driven by gravity. Thus, in the headworks, you are going to have the relevant pumping station to pump the relevant water to the relevant head, such that you are going to also take into account the friction losses and such. Then we looked at removal of grit and such, core screens and so on and so forth. But in the context of grit removal, we looked at briefly sedimentation, right? Grit, relatively much bigger particles compared to the other suspended particles, let us say, right. We talked about sand, we talked about I believe coffee beans and so on and so forth. So, we talked about core screens or such, yes, but we also talked about rectangular basins, where you have laminar flow conditions with a weir at the end, right, proportional weir or such that the flow is maintained, constant flow, such that scouring of only the suspended particles or organics is taking place, but the relatively heavier particles which is the grit is settled down, right. We looked at this. In that context, we looked at this term or came across this term sedimentation. So, in the next couple of sessions, or at least in this session, we are going to look at sedimentation in greater detail, because that is one of the primary treatment process that is going to remove most of your suspended particles in wastewater or water, let us say, depending upon the kind of water anyway, right. So, let us look at what we have here. As I mentioned, we are going to look at sedimentation and contents, at least of this particular session and probably the one after this session. So, why is it that what do I want to achieve out here, right? So, we have suspended particles, relatively bigger, some smaller, some of these are inert, some of these have organic content, right. So, inert, if you do not remove them, they will cause issues down the line in the other unit process by settling out, right, and such, and you are going to have relatively lesser effective volume. Also can lead to abrasion and wear of tear of your relevant machinery. Yes, so you do not want the inert content, and typically the bigger or heavier inert content we remove during preliminary treatment or during the headworks, right. So, that is when we already remove most of the bigger inert particles, but there will be some suspended inert particles and also which are relatively smaller than grit, and you will also have some organic content which is suspended. So, organic content, how do we remove typically? Typically, we will remove that by a biological process, where microbes in the presence of oxygen are going to catalyze this reaction of oxidation of your waste. Our waste is the microbes' food, right. Our waste by oxygen, oxidation of our waste by oxygen, and the reaction is catalyzed, or the kinetics is improved by the enzymes released by the microbes. But here obviously oxygen needs to be supplied. So, we are going to have to pump oxygen or air into the relevant biological process. So, when we are pumping air in, obviously that is going to be a costly affair. So, if you have the relevant sludge treatment available out there, you can remove a significant fraction of your organics here, not a lot, but a significant fraction of your organics here, so that less load is available on the relevant or in the biological process, bringing down the cost. But again, it is not as straightforward as that, you have to look at other aspects too. Okay, so, we are going to look at sedimentation, right, and in the context of sedimentation, depending upon the type of flow conditions, the type of particles, you have different types of sedimentation, right. So, one is discrete, and we looked at this in the context of grit removal. When we say discrete, I guess people know what discrete means. So, in this context, we can think of it as settling of the relevant particles independent of each other, right. The particles which are settling do not do not interact with the other particles, let us say, right. So, that is layman's term. So, typically we see this when we are looking at removal of grit, but again type 1 settling, again all these are ideal case, what do we say, scenarios, and you are never going to have one what do we say, perfect example of discrete sedimentation. The second one, which we are now going to look at in the context of primary treatment of wastewater, as in when you want to remove these particles, let us say, which are not as big as grit or not as heavier as grit. So, you are going to look at flocculent settling, right, wherein these smaller particles, relatively smaller particles, let us say, by themselves they will take too much time, let us say, to settle down. So, what do? You add a coagulant, or if the particles are good enough to be or not good enough, or are going to settle down without the presence of or need for a coagulant, that is also one possibility, especially in wastewater. But let us look at both the aspects. Typically these have charge and they do not let them come together, let us say, they repel, right, negative charge, they repel. So, if you want them to come together and coagulate and then form flocks, what do you need to do? You need to add charge. So, you are going to add the opposing charge, which is a positive charge. So, that is where when you look at addition of this is plus, I guess that might not be clear due to the way it is being written. So, I am going to add a coagulant can be Al3 plus, right, Fe3 plus, Fe2 plus, yes. So, now I am going to neutralize the charge on these colloids, so coagulation, and then these colloids now come together and form flocks, right. So, flocks, and then these flocks settle down, and that is typically the case in flocculent settling, right. And sometimes if or depending upon the size, without the addition of coagulant 2, you can have flocculent settling, right. And this is also seen in case of your primary sedimentation tank, right, but that will also encompass what do we say, hindered or compression sedimentation, but we will look at that later. So, flocculent settling, type 1 and type 2 settling, and then hindered, right, and compression, which we will look at in some detail later. Once we understand these relevant types of sedimentation, we are going to look at the relevant variables and look at the relevant design, let us say, right. What are the variables of interest and how do we design, let us say, right. Let us move forth. So, the sedimentation, so water as we know flows into the settling tanks where the flow is devoid of turbulence. Again we are talking about turbulence and laminar flow. So, what do I understand by that? Laminar flow, more or less it is quiescent flow, as in the flow goes through in layers, where there is little interaction between one layer to the other. There is little to no interaction between one layer to the other. But turbulence, let us say, you see that usually, let us say, when you have monsoon or during the monsoon season, and if you look at the canal, you are going to look at turbulent conditions, let us say, it's the flow is going to be violent, you are going to have eddies and such, and it is not certainly going to be laminar, right. Here we are talking about, at least in this context, we are talking about what is this now, laminar flow. Why? I guess if you have turbulence, the scouring velocity and such, the particles are never going to be able to settle down, right. The eddies, let us say, they are going to keep the particle up in suspension because they are going to be what we say carried along with the fluid of or fluid flow. So, typical retention times are from 2 to 8 hours, and what happened to these flocks or the particles, they settle out, and that is what we refer to as sludge. Let us say if this is my sedimentation basin, so the bigger particles, let us say, are going to settle down, right, and this settled out, right. What do we say, fraction, we are going to call it as sludge, one of the primary treatment stages, what, sedimentation. Again here we are not looking at coagulation or flocculation, that you are going to look at as and when needed. Here we are just talking about settling basins only, right. Let us move on. So, this is a typical picture. Obviously, the flow you see is pretty still, right. If you have turbulent conditions, obviously your particles are not going to what do we say settle down, or maybe think of what do we say this room here. If I bring some dust in my or fine dust in my hand and throw it up into the air, as in keep it in suspension, and now the room is entirely locked, there are no fans running here and such, right. So, the particles are going to settle down, let us say relatively faster. But once I throw this dust up into the air and I turn on the fans, I am going to create turbulent conditions, right. So, the particles are going to remain in suspension for a much greater period of time. That is one aspect, or that one way to understand why we are going to maintain these laminar flow or quiescent conditions, right, typical sedimentation basins. Let us move on. So, I guess I wanted to show a video here, and what is the who is providing us with this video? It is American Waterworks Association, right, and just let us look at what we have, and I will try to give the voice over. So, sedimentation and clarifiers, okay, fine. So, what is happening here? As you can see, the relatively bigger particles were settling down, right, relatively bigger particles, they were settling down, right. I will fast forward as deemed necessary. So, relatively bigger particles or heavier particles are settling down, right, I should not just say bigger. And here you have relevant quiescent conditions or laminar flow conditions, and you have the waves here all along. So, that this velocity is, or is more or less is in the laminar flow region, let us say, right, or this flow is in the laminar flow region, and you are going to have the relevant settling during this particular period, let us say, right. And you can have rectangular or you can have circular, what do we say, sedimentation basins. Let us, I think we are going to look at the weirs. So, here you have the weirs, let us say, yes, different kinds of designs, we will look at that later. So, an example of a circular one, which we will come back to looking at. I believe we have a better picture. Okay, here we have the sedimentation, circular sedimentation basin or circular clarifiers, let us say, right, that is what you see. There are two kinds of what do we say, circular sedimentation tanks. One is where the flow comes in through the center from the bottom to the top and flows radially, or again perimeter, what do we say, flows in from the perimeter. But typically in India, I have seen that most people use the ones that come in from the center, flow up and flow out. Again, we will look at the relevant schematic or graphic later, right. So, I guess this is what we want to look at. So, particular what do we say, schematic of this sedimentation basin, the circular sedimentation. So, water is coming in through here with the relevant suspended particles, and this influent zone, what is it that we are trying to do? We are trying to see to it that the velocity, which is relatively higher here, by the time that it comes out here, let us say, right, comes out here, what is going to happen to that in the influent zone? What do we want to do? We want to see to it that the velocity of water comes down, or the energy is dissipated, right, that is the major aspect, energy is dissipated, and there is uniform distribution of your relevant what do we say, flow and the suspended solids. So, that is what we want to do in our influent zone. And then here we are going to have this settling zone. Please note this, because we are going to make some assumptions later. So, this is where some particles are going to be settled down as the water flows radially from the center towards this effluent zone. Effluent zone, again the design has to be such that the particles that have settled out are not carried over into the effluent zone, right. So, that is something to keep in mind. So, influent zone, effluent zone, settling zone, and then we should also have another zone. This is called the sludge zone, let us say, right, where the sludge is collected, and then you have the hopper here. You see the hopper that is going to scrape your sludge, and that is going to be collected, let us say, the sludge that is collected at the bottom is going to be collected. So, what do we have? Again, different kinds, we can have them inside or such, right, circular. Let us move on, and let me move on to one aspect I wanted to show. Okay, to increase the surface area available, we will look at why that is needed. As in height of your, unlike what we might think, height does not really play a role. Let us say height of your basin does not really play a role in determining the removal efficiency of your relevant, what is this now, settleable solids, let us say. but the surface area does, but again we will look at this later. So, to improve that, you can have what do we say, plate collectors and such, and I believe that is what we are going to look at, right, different plate collectors here, right. So, that the height, let us say, is going to be pretty less, not let us say meters or so, but only a few centimeters, and you will still have the removal. So, that is what you see here. So, more surface area, the settlable solids are going to settle down in this plate or circular collectors, and they are going to settle down out there, and depending on the relevant design, the sludge is going to be carried down, right. So, enough of that, let us move back to our presentation. So, that is one schematic. So, different types of settling, the ones we looked at until now were mostly type 2 settling, but I just wanted to show the kinds that we are discussing here, right. So, type 1 or discrete settling, what are the major aspects? As I mentioned, the particles are not interacting with each other, they settle as discrete particles, right. So, no interference, and more importantly, when there is no interference with each other, no flocks are formed, as in one particle is here, they just go through like this, as in they do not come together and they do not form flocks. This does not happen in type 1 settling, let us say discrete settling. So, where does this occur? In pre-sedimentation for sand removal, grit removal, or coagulation in surface water plant, let us say, okay, in surface water plant. Again, filtering bed, settling in a grit chamber of the wastewater treatment plant, as we mentioned earlier, let us say, right. Let us move on. So, as we know, right, gravity is pulling us down, it keeps everybody down to earth, right. So, here we are going to look at Stokes' law, which more or less again looks at what do we say, application of gravity, right. And what do we have here? Let us say we have relevant particle of different any size, let us say. What is going to happen? The gravity is going to pull it down, and the buoyancy, I guess, is going to push it up, right. This particular drag force, or let us say the frictional force on the relevant particle, right, gravity minus buoyancy. So, at the terminal settling velocity, when there is no acceleration, right, will be equal to this, right. This force pulling it down will be equal to the frictional force, let us say. So, you can think of that. So, we can just apply it, and what is it obviously going to be depend upon? It is going to be depend on the density of the water, density of the solid, the relevant shape, the relevant volume, the relevant surface area of the particle, and then the coefficient of drag. I think okay, we have that, and we can plug that in and get a relevant equation. And for a spherical, right, here for a sphere, right, we can have the relevant what do we say, settling velocity, which we will derive from this equation. That is going to be this. So, let us look at what are the relevant variables here. So, settling velocity or the terminal settling velocity of that particle. So, obviously, as we mentioned, what is it going to be depend upon? Obviously, gravity, that is a constant, but what are the relevant other constants here? Density of the sphere is a variable, obviously, density of water is relevant constant, right, and what else? Density of water out here, right, coefficient of drag, and then the diameter of the sphere. As I mentioned, we are modifying the equation we get from this particular derivation for a sphere, let us say, right, and that is what we have out here. And this is applicable in general everywhere, but again we are going to look at applications in the context of sedimentation for laminar flow, right. Let us look at what we have out here. So, discrete settling. So, again as I mentioned, the gravity and buoyancy is going to be, what do we say, the force pulling it down or the particle being pulled down will be balanced by the drag force or the frictional force. And Mr. Stokes, so thus the Stokes' law will give us this equation, but in which conditions is this equation what do we say, relevant? Let us say it is relevant when the flow is laminar, and in general for determining whether a flow is laminar or turbulent or in between transitional flow, we look at the Reynolds number. So, if the Reynolds number is less than 1, the flow is deemed to be laminar flow, right. So, we will apply the Stokes' law only when the flow is laminar and the particle is a sphere, let us say. So, that is something for us to what do we say, keep in mind. So, look at this, and again you can look at this equation too, let us say, right. So, that is what we have again only for laminar flow. So, one aspect to note is that this Reynolds number is depend upon the diameter of the particle, the kinematic viscosity and the settling velocity of your particular particle, right. So, what does it depend upon? Let us say water, let us assume this is constant function of the diameter and the settling velocity. Let us keep this in mind, we will come back to this again, right. So, here from this particular reference, what do we have? We have the relationship between Reynolds number and the coefficient of drag for different spheres, let us say different types of particles, spheres or different shaped particles, pardon me, discs and cylinders. So, again you can look at the relevant equation and understand this. So, again you see that for differently shaped particles the behavior is going to be different. So, here we have the laminar region, yes, when the Reynolds number is less than 1, right, and then here we have the relatively turbulent conditions, let us say, right. And again we are just trying to look at the different profile, because as we see it is dependent upon the shape of the particle too, right. So, here is the coefficient of drag which is decreasing with increasing Reynolds number. Let us move on, and this is from the Davis book, and what do we have? We can calculate our the coefficient of drag in terms of the Reynolds number. So, for relatively higher what do we say Reynolds number where the flow conditions are turbulent, I believe coefficient of drag will be something like 0.4 if I am not wrong, right, we can check this later. But in the laminar flow region, right, the relevant coefficient of drag will be equal to 24 by r, right. So, again coefficient of drag is 24 by r, and we know that Reynolds number is equal to the diameter of the particle, settling velocity of the particle by the kinematic viscosity, let us say, right. So, that is something to understand out here. So, what do we have? We have the equation for coefficient of drag in the laminar flow conditions, coefficient of drag out here in the transitional flow, right, and here we have the profile for the Stokes law which is applicable only in the laminar flow conditions. So, again we have coefficient of drag on the y axis and Reynolds number on the x axis. So, here we have laminar flow and then some transitional flow and then turbulent conditions out here, let us say. So, what do we see? We see 3 kinds of data here, at least in this particular initial what do we say part of the graph, initial half of the graph, spheres observed, right, and the relevant equation, and then for the Stokes law, let us say, right. So, what do we see out here? We see in the laminar flow conditions obviously there is a good agreement between observed and the relevant laws and the equations, but then you see the divergence being apparent in the transitional and certainly in the turbulent conditions, let us say, right. So, again in the type 1 settling we are concerned with the relevant laminar flow only, and for spheres that is something to keep in mind, right. So, let us move on. Okay, so, laminar flow Reynolds number, coefficient of drag is dependent upon the Reynolds number, and transitional flow and so on and so forth, let us say, right. Okay, as I mentioned 0.4, that seems to be the right value, and I believe we calculated the Reynolds number to be equal to not calculated, we know that it is equal to the diameter of the particle, settling velocity by the kinematic viscosity. So, now how do I get this settling velocity? So, I have my Stokes law, relatively simple, but as we know Stokes law is applicable or very well applicable only in the laminar flow region, that is what I see out here. So, assuming laminar flow conditions, I am going to calculate the Stokes settling velocity from the Stokes law, okay, for that particle shape and not shape size, let us say. Based on that I am going to calculate the trial Reynolds number. If this trial Reynolds number ends up being less than 1, fine, I can go ahead with my relevant calculations and such. But if this Reynolds number turns out to be more or much more than 1, then what do? It is an iterative process, right. As in with this Reynolds number I will calculate the coefficient of drag whether here or here, right, and then go ahead and calculate the relevant settling velocity from the Newton's equation if I may, and then I will again calculate the Reynolds number and see whether that's what we say more or less applicable to my particular case, or do I need to again change the relevant coefficient of drag, and then I will come up to a particular point again iteratively, where I can come up with my or calculate my settling velocity and the Reynolds number, right. So, that is something that I can do out there, right. So, that is something to keep in mind. Let us move on. So, ideal sedimentation basins, there are some assumptions. First thing is we are talking about type 1, that is why discrete, and then as we looked at the relevant what do we say video, we have inlet zone, outlet zone, sludge and settling. All these are general aspects. As I mentioned, inlet zone we are going to try to achieve even distribution of flow, but that is not always possible, and this outlet zone we are going to say again even what do we say distribution of flow when it is leaving the settling zone. But one aspect which we will look at later is that we assume that the particles are uniformly distributed throughout the depth of the relevant tank, as in let us say this is my tank and here is my flow rate, and this let us say is my settling zone. So, what I am saying is all these particles which are bunched together at the inlet are going to be uniformly distributed across this particular depth of the settling zone, let us say depth of the inlet zone, let us say, right. So, that is something to keep in mind, and particles that enter the sludge zone are captured and are not scoured back up. Particles that enter the outlet zone are always removed, that is something we need to look at or consider. So, particles that enter this outlet zones, as this is the settling zone and this is the outlet zone, and if a particle is deemed to have entered here, we assume that it is leaving the system. So, let us look at the common types of sedimentation basins. Here we have upflow, right, upflow, yes. So, what do we have here? Fluid is coming up at this particular point and velocity of your particular liquid is given here, and this is the settling velocity of your relevant particle, which you will calculate from your Stokes law, let us say. Initially the velocity is higher here, but out here at the top I am increasing the surface area, right. So, what will that lead to? I know that Q is equal to the velocity of that particular liquid into cross sectional area. So, for a smaller cross sectional area the velocity will be higher, but if I increase the relevant cross sectional area for the same flow rate, what is going to happen? The velocity is going to decrease, velocity of the relevant flow rate is going to decrease. So, that is what we see here, it is relatively higher, and here with a greater surface area, right, the velocity of your particular fluid flow is going to decrease, let us see. Why is that necessary? Because if not, if the fluid flow is pretty fast and my settling velocity is this or relatively lesser, right, obviously the particle will not be removed or will not be settling down, but the R net is going to be such that the particle is going to flow out with the relevant liquid, right. So, only if my settling velocity is greater than this particular VL, if I may call that out here, right, VL, will my particle be removed, right. So, that is something to keep in mind. So, let us see or let us look at some of the terms out here, okay, maybe I will look at that later. So, we have different kinds of upflow, right, different kinds of upflow, and then we have what do we say rectangular sedimentation basins too. Let me discuss this in somewhat greater detail. So, what do we have? We are talking about upflow sedimentation basins, right, and what am I concerned with? The velocity of flow of the liquid and the settling velocity of the particle, which I will calculate from my Stokes law, which we discussed earlier, and Stokes law as we know is only valid for laminar flow conditions, that is something to keep in mind. So, what is the velocity of this liquid going to be depend upon, right? It is going to be equal to what now? The flow rate of the relevant liquid, flow rate Q, right, units can be meter cube per second or volume per time, let us say, right, volume per time, by the cross sectional area. Which cross sectional area am I concerned with? This surface area at the top, I am going to say that is AS. So, what do I have? This is nothing but the overflow rate, right, surface overflow rate, that is something for you to keep in mind, right. So, this is the surface overflow rate, right. So, if my particle settling velocity is greater than or just equal to the surface overflow rate, 100% of the particles will be removed, right. All those particles with a settling velocity greater than my surface overflow rate, right. Again, this is the surface and the velocity at this particular point, I guess we are calling that to be the surface overflow rate, right. The flow is going in this direction because it is upflow. So, if all those Vs having greater than or equal to or being greater than or equal to V naught, right, will be removed. Those particles with a settling velocity less than V naught will not be removed, everything or 0% will be removed, right. Either it is 100% or 0% removal, though in practice it will not be the case, but theoretically that is what we see, right. Let us see what we have. Upflow clarifiers, that is what we just discussed, and overflow rate, or I guess another term I should have mentioned earlier, hydraulic, as in water surface loading, let us see, overflow rate or hydraulic surface loading, and these aspects we just discussed. Let me move on. So, this is with respect to upflow. What was the second kind that we came across though? We came across the rectangular, what do we say, sedimentation basins, or the flow in the horizontal direction, let us say, even for circular basins, let us say. So, there we are only concerned with the settling zone. I am not concerned with the inlet zone, I am not concerned with the outlet zone, but one aspect to remember is that all the particles we are assuming are uniformly distributed, and any particle that is not within this sludge zone, which is at the bottom, right, and which leaves this settling zone, even here is assumed to leave the relevant system. That is something to keep in mind. So, let me what do we say, note down a few variables here. Let us say this height is h and length is L, and if I look at the top view, right, this is the length and the width is this, let us say, right. So, what do I need to look at now? Let us say my particle is coming in out here, right, and the worst case scenario, not worst, if it is just about to be captured, it can travel, you know, it can, even if it comes till here, we are assuming that it will be captured, let us say. So, what is it that is available, or what is it that it needs to do, the particle I mean. So, it needs to traverse a distance of h during the time that this particular water or particle stays in this particular tank, let us see, right. So, that is what we have, right. So, let us see, you know, what it is that it is dependent upon or such, this velocity, let us see, h by time for detention, let us see, right. But what is h? I mean, h is the height, and what is this time of detention? How will I get that, let us say, right. Time, how can I get that? Let us say I know that q is volume per time, let us say, right, q. So, if I say it is v by q, right, volume by volume per time, so I can get the relevant time. So, I need to divide by v by q, pardon me, this is not theta, it should be q. So, that will be equal to h q by volume, let us say, right. And what is the volume going to be equal to? Let us look at it, h into q, volume equal to length into width into height, let us say. So, what is going to cancel out? Yes, height, and what are we going to end up with? It is q by L w, right. So, that is what we have out here, right. So, as you see here, first aspect is that though it seems counterintuitive, this velocity, let us say, that we are calculating out here, which will give us an idea about the cutoff for the relevant particles, right. It is again similar to the relevant surface overflow rate, which we calculated for the upflow relevant upflow clarifiers. There too we had our surface overflow rate was q by surface area, and here too you see that this is nothing but q by the surface, let us say, right, surface, right, surface area. So, this is our, what do we say, surface overflow rate for the rectangular basins. But unlike the case of the upflow clarifiers, upflow is where we have the flow up there. For the flow where we have, I mean where the flow is horizontal, we are not going to just have 100% removal or 0% removal. This is not going to be the case. Why is that? Because here the assumption is that all the particles are uniformly distributed across the height or this particular cross sectional area, let us say, right. So, if a particle that comes out here with a settling velocity just equal to v naught, that will be removed, fine. But if it comes out here, let us say or with a lesser one, let us say, I guess I should have drawn a better figure, or let us say it has to be such that Vs is V naught by 2 or 2 Vs is V naught, let us say, and this particle is out here, right. So, this particle, let us say, is traveling at a Vs such that it will just be removed at this point, right, but we see that it came in at h by 2. But what about the particle that comes in at h, that will not be removed, right, this parallel line, let us say, as we can see, that particular what do we say, that particular particle which comes in at height h will not be removed, as you can see, it is going to leave, right. So, we are not going to have 100% or 0% removal, but we are going to have fractional removal. So, that is going to be given by Vs by V naught into 100%, the percentage removal, I guess, right. So, that is something that we will have to look at. So, what do we have? Rectangular basins, particle removal is dependent on the overflow rate, which we just looked at, and obviously as I mentioned, or we mentioned, settling velocity, right, settling velocity must be sufficient that such that it reaches the tank or the bottom or reaches this sludge zone, right, during the time that the water resides in the tank. That is something that we looked at, and what did we do? We calculated this and we came up with our surface overflow rate, right, and we looked at this particular case as in V naught out here just captured, and if the settling velocity is such that its Vs equal to V naught by 2, I guess that is what I corrected earlier, is not it? Okay. So, I should have written it the other way then, I guess, right. This is for the case where we were talking about h and h by 2, right, where the settling velocity is relatively lesser, let us say, and it is lesser such that earlier case we looked at Vs equal to V naught, and now we are saying Vs equal to V naught by 2, let us say, right, V naught by 2, right. So, what do we have? If it comes in at h by 2, we see that it will be captured, but that fraction of the particle which is above, let us say, it will not be captured, right. These flow paths are going to be like this. So, this is escape, this is escape. So, that is why we will not have the 100% or 0% removal as discussed in the upflow clarifiers, but we are going to have a percentage removal, and that is what we see out here, let us say, right. So, let us move on. So, circular sedimentation basin 2, what is it that we see? We see that it comes up in the center and then flows radially here, again horizontal flow itself. And typically if we look at the relevant design, the rectangular basins make the best use of the relevant cross sectional area or the area available, let us say, right. But the what do we say, circular basins are preferred because relatively low maintenance, let us say, again this is with respect to the hopper system, I guess, right, and relatively low costs. So, thus people go for the relevant what is this, circular sedimentation basins. But if you are looking at the design and the effective use of the what is it, area, the rectangular basins are typically better, right. That is a no brainer if you can think of this, what we have out here and the particle distribution radially, let us say, right. So, that is something to keep in mind. So, we are going to look at effect of depth on removal ratio, but looks like I am almost out of time. We will discuss this in the next session, but again we were looking at type 1, and in that context we saw that the critical aspect is the surface overflow rate, let us say, right, both for your upflow and for your rectangular basins. Yes, and thanking you for your patience, I will end today's session.